Welcome to the Deep Dive. Today we're tackling a big one. Advanced artificial intelligence systems.
Yeah, it's a topic you hear everywhere, right? AI this, AI that.
Exactly. But we want to go, a bit deeper than the headlines, really unpack what makes these sophisticated systems work.
We'll be drawing on some pretty cutting-edge stuff, like research into what's called meta AI, and also looking at insights from Germany's national AI strategy.
Right. And the goal for everyone listening who wants to get smart on these complex topics quickly, but thoroughly.
Without getting totally swamped in jargon.
Yes. We want to give you those key aha moments, sort of a shortcut to understanding this field.
Sounds good. And maybe the first aha moment is realizing we're not just talking about one single monolithic AI anymore.
Okay, tell me more. What are we looking at instead?
Well, the research, especially around meta AI, points towards systems built from many different AI components. Think of them interacting, working together.
Like a team.
Pretty much, yeah. The meta AI papers mention concepts like compare or hypersia. These aren't just scaled-up versions of today's AI.
So it's a fundamental shift.
I think so. It demands new capabilities, things we don't see as much in simpler AI, like self-awareness, the ability to dynamically assign roles within the system, even ethical reasoning built in.
Okay, that sounds like a lot to cover. This meta AI research highlights some key directions, right, for making these complex systems actually work.
Absolutely. The analysis lays out 7 key research areas. We won't hit all 7 today, but we'll dig into several core ones to build a clearer picture.
So what's on the agenda?
Right. First up is computational metacognition.
Okay.
Basically, AI that can think about its own thinking.
Intriguing.
Then we'll look at formalizing dynamic placeholders, sometimes called placebo pipes, which is a bit of a funny name.
Placebo pipes.
It's about flexible role assignment. We'll also cover why precise communication protocols are so vital for these multi-part systems.
Makes sense. Coordination is key.
Definitely. And we'll touch on formal languages for precision, how you even evaluate if these complex beasts are working well together.
Right, effectiveness and cohesion.
Exactly. And maybe briefly touch on ethical integration and architectural choices, like centralized versus decentralized control.
Okay, quite a journey. Let's start with that first one, computational metacognition. AI thinking about thinking. It sounds a bit sci-fi. What does it actually mean practically?
Yeah, it sounds abstract, but it's really about an AI's ability to monitor and control its own internal processes, its own cognition.
So it's watching itself think.
In a way, yes. It's not just about reacting to the outside world. It involves an internal feedback loop. The AI reflects on how it's reasoning, how it arrived at a decision.
And the goal is?
To improve, to get better at thinking, essentially, to adjust its behavior based on that self-reflection. It's like the AI saying, that prediction was off. Why did I think that? And then changing its internal approach.
So it's learning from its own mental mistakes, not just from new data.
Precisely. And there isn't just one way to build this. The research talks about different computational metacognitive architectures, CMAs, different blueprints for this self-reflection.
Examples?
Well, there's MIDCA, Metacognitive Integrated Dual Cycle Architecture. It has distinct cycles for acting and then reflecting on that action.
Okay.
Then there's C4 modeling, which tries to use semantic knowledge, like ontologies, to build AI that's not just effective, but also trustworthy because it can explain itself in human terms.
Linking metacognition to explainability, that's important.
Yes. The key takeaway is that advanced AI is experimenting with different internal operating systems for self-monitoring, not just sticking to one model.
The research also mentions EDCR, error detecting and correcting rules, and something called MACO for large language models.
Yeah.
How do they fit in?
Right. EDCR is specifically focused on perception, helping an AI spot and fix errors in, say, what it sees in an image. It learns rules like, if I see this pattern, it's likely an error, so adjust.
Okay, self-correction for sensory input.
Yep. And MECO, that's metacognitive control for LLMs, is interesting. It lets a large language model use internal cues, sort of like a feeling of knowing, to decide if it needs help.
Help, like asking a human.
Or, more often, deciding whether to use an external tool like a calculator or a search engine to get a better answer without needing specific retraining for every tool. It senses its own uncertainty.
So it knows when it doesn't know something reliably.
Exactly. These are all ways to make AI more robust by building in mechanisms for it to catch and fix its own potential flaws, either in seeing, reasoning, or generating language.
Okay, this drive for self-correction seems crucial. Now, you mentioned different types of metacognition. What are the main flavors here?
Yeah, the research often distinguishes between explanatory and anticipatory metacognition.
Okay, backward-looking versus forward-looking.
Pretty much. Explanatory metacognition kicks in after something happens, usually a failure or an unexpected outcome. The AI analyzes why it happened.
Like a postmortem.
Right. It might compare its prediction to reality, diagnose the error using what are called meta-explanation patterns, and then set itself new internal goals to avoid repeating the mistake.
And anticipatory.
That's about looking ahead, judging its likely success before acting. Can I solve this problem? How confident am I?
And if it's not confident,
This is where it gets really interesting. It might decide not to tackle the task itself. It could potentially delegate it to another agent, maybe another AI component, or even a human if it anticipates failure.
wow, that implies a pretty sophisticated understanding of its own limits.
It does, and it touches on ideas related to theory of mind, the ability to reason about the capabilities and mental states of other agents. If I know Agent B is better at X and I predict I might fail at X, I should ask Agent B.
That's a huge leap. How does AI introspection fit into this picture? Is it the same as metacognition?
Closely related, but maybe slightly different. Introspection is more the ability to examine internal states and processes. Metacognition is the use of that ability to monitor and control.
Gotcha. So introspection enables metacognition.
You could say that. And it's fundamentally linked to explainable AI, XAI. If an AI can introspect, look inside itself, it can then generate explanations.
Makes sense. You need to see the workings to explain them.
Right. And the research notes different levels of explanation. You might have introspective tracing, super detailed, step by step. Here's exactly how I reasoned.
Like showing your work in math class.
Exactly. Or you might have introspective informative, which gives enough information for a user to understand the gist, assess trustworthiness, spot potential issues, but without drowning them in every single detail.
Finding the right balance for usefulness. So how do these systems actually build this self-awareness? What are the nuts and bolts?
There are several mechanisms being explored. One is self-modeling. The AI literally builds and maintains an internal model of itself, its identity, its abilities, maybe even its past experiences.
An AI autobiography, almost.
Sort of. Robots learning models of their own bodies is a simpler example. Then you have more practical self-evaluation components, chain of thought or COTI analysis. You see this with LLMs forcing the model to show its work, articulate its reasoning step by step. That makes it much easier for the AI itself or an observer to spot logical flaws.
Okay, making the thinking transparent.
Exactly. Then there are error identification mechanisms. Things like self-consistency checks. Does my answer make sense based on what I said earlier? Or using external knowledge retrieval to verify facts. Tracking uncertainty levels like entropy. Some systems have dedicated validation modules.
Lots of cross-checking.
Self-reflection is another big one. The AI critically analyzing its own outputs, its reasoning process, its decisions, explicitly aiming to improve next time.
A built-in quality control loop.
You got it. And finally, there are more general evaluation frameworks. Setting clear goals, using diverse test data, tracking multiple performance metrics over time, and often, crucially, including human oversight. Think of services like Google's Vertex AI Gen AI evaluation providing tools for the systematic assessment.
Okay, so a whole toolbox for self-assessment. What about robotics, specifically? You mentioned self-awareness there, too.
Yeah, in robotics, researchers talk about capacities like self-evaluation, a robot knowing that it knows how to do something and when it's appropriate, and meta-reasoning, the robot consciously thinking about its own reasoning, its goals, maybe alternative strategies.
So a robot could think, okay, I need to pick up that object. Method A is faster, but method B is safer, given the context. I'll choose method B.
That's the kind of capability we're talking about. And all this self-awareness feeds into something called proactive issue identification.
Meaning it spots problems before they happen.
Ideally, yes, because it can analyze past failures, monitor its current performance, and use predictive techniques. Predictive AI can look at historical data and real-time metrics to forecast potential issues, performance drops, resource bottlenecks, maybe even hardware failure.
Like predictive maintenance, but for the AI's own operations.
Right. Anomaly detection can flag weird behavior that might signal a problem. Proactive threat detection for security. Some advanced systems are even aiming for self-healing capabilities, automatically fixing certain types of errors.
So the AI isn't just reacting, it's actively trying to keep itself running smoothly and effectively.
Exactly. It's anticipating and trying to mitigate issues.
Okay, let's tie this back to meta AI and understanding these advanced systems. What are the big implications of all this metacognition research?
Well, first, for complex meta-AI systems with lots of different parts, you'll likely need a hybrid metacognitive approach, different techniques for different components.
Makes sense. Not one size fits all.
Second, it signals a big shift from purely reactive error correction to proactive self-management. The AI is becoming more autonomous in maintaining its own quality.
Taking responsibility for itself, in a way.
Sort of. Third, introspective tracing, that detailed reasoning path, becomes really important for debugging these incredibly complex systems and for accountability. If something goes wrong, you need to be able to trace why.
Essential for trust.
Absolutely. And finally, the idea of self-representation, the AI having a model of itself, could significantly improve how it reasons about its role within the larger system and how it interacts with other components, understanding its own place.
That provides a really solid foundation on the self-awareness side. Now let's shift gears to these placebo pipes. Formalizing dynamic placeholders. What's the core idea here?
Right. Placebo pipes, it's about dynamic placeholders in the AI's architecture, or maybe its internal communication language. Think of them as designated empty slots.
Empty slots.
Yes, slots that aren't filled when the system is designed, but get filled at runtime when the system is actually operating.
Filled with what?
Could be specific AI agents, could be software components, particular algorithms, configurations, even specific data values needed for a task.
So it allows for flexibility. Assigning resources on the fly.
Exactly. It contrasts sharply with static systems where everything is hardwired from the start. These placeholders represent something that will be specified or bound later, dynamically.
Okay, I get the concept. But why the emphasis on formalizing them? Why formal methods?
Because with this level of dynamism in a complex system, ambiguity is your enemy. Formal methods use mathematical techniques, logic, set theory, automata theory, to rigorously model, specify, and verify system behavior.
Bringing mathematical precision.
Precisely. For placebo pipes, formal methods let you define unambiguously their syntax, how you write them, their semantics, what they mean, their scope, where they apply, any constraints, what kind of thing can fill the slot, and crucially, the rules for binding them, how the system decides what goes into the slot at runtime.
So it eliminates guesswork and potential misinterpretations.
That's the goal. It's about ensuring predictable, verifiable behavior even with dynamic parts.
How do these placeholders relate to the actual roles or capabilities needed within the Meta AI system?
You can think of a placebo pipe as representing a required role or a capability slot that needs filling for a particular task.
Like, we need an agent capable of image analysis right now.
Exactly, and the research points to things like attribute-based access control, or ABAC, as a good model for managing this.
ABAC, I know that from security.
Right, similar principle. Instead of assigning Agent X permanently to the image analysis role, ABAC uses policies which can themselves be formally defined to dynamically assign an agent to fill that pipe based on attributes.
Attributes like?
Skills. Is this agent good at image analysis? Current workload. Is it busy? Maybe trustworthiness. Has this agent performed reliably? And also the context. What kind of image? How urgent is it?
So it's highly context-aware and adaptive assignment.
Very much so. And this ties into self-optimization.
How so?
Well, self-optimization is the system's ability to continuously adapt and improve its own strategies or configurations based on performance feedback or changing conditions. It's vital for resilience and efficiency.
Okay.
So in the context of placebo pipes, the AI system could learn over time. It figures out which specific agent or algorithm or configuration, when plugged into a particular pipe, leads to the best results under certain conditions.
It learns the best way to fill its own slots.
Yes, through techniques like reinforcement learning, or maybe specialized methods like self-alignment optimization, SAO for LLMs, or dynamic algorithm configuration, DAC. Performance feedback drives the process. The AI dynamically tunes its own internal structure based on what works.
Constantly tweaking itself for better performance. Okay, so let's synthesize this. What are the main implications of formalizing dynamic placeholders for understanding advanced AI?
First, unambiguous definition is critical. You need formal methods to specify these pipes and their binding rules clearly. Any vagueness is a recipe for disaster in such complex systems.
Clarity is paramount.
Second, ABAC provides a powerful model for managing the assignment to these pipes based on agent capabilities and context. It's a good fit.
Makes sense.
Third, self-optimization is the engine that drives the dynamic instantiation. It uses performance data to learn how to best fill these pipes over time.
The learning mechanism.
Exactly. And finally, remember that placebo pipes aren't just for simple data. They can represent abstract functional roles, the planner, the monitor, or even adaptable interaction protocols between components. It's a very flexible architectural concept for building modular adaptive AI.
Okay, that adds another layer of sophistication, dynamic internal structures managed formally.
Hmm.
What about how these different components talk to each other? Communication must be critical.
Absolutely essential. If you have multiple AI agents or components needing to coordinate, especially for complex tasks like delegation, they need precise and reliable ways to communicate.
Not just sending raw data back and forth.
No, much more than that. We're talking about agent communication languages, or ACLs, and interaction protocols.
ACLs.
Think of them as specialized languages designed for software agents to exchange complex information, intentions, and commitments. They often draw on speech act theory from philosophy of language.
Speech acts, like informing, requesting, promising.
Exactly. An ACL message typically specifies the sender, receiver, the content of the message, but also performative or speech act, what the sender is trying to do with the message. For example, inform, request, propose, agree.
So the intent is explicit.
Right. ACLs also rely heavily on ontologies, shared vocabularies, and conceptual frameworks, so agents understand the terms being used in the content. And interaction protocols define the allowed sequences of messages, like a script for a negotiation or an auction.
Are there standards for this?
Yes, the most well-known is the FIPA ACL standard. FIPA stands for the Foundation for Intelligent Physical Agents. It provides a standard message structure and, importantly, formal semantics.
Formal semantics, meaning the meaning is mathematically defined.
Correct. FIPA uses a formal language, often based on modal logic, called FIPA semantic language, SL, to precisely define the conditions under which an agent can truthfully and rationally send a certain type of message and what the expected effect is. This removes ambiguity.
That sounds rigorous. Is that the only approach?
No, another important approach, particularly relevant for managing tasks and delegation, is commitment-based protocol.
Commitments, like promises.
Pretty much. Instead of just focusing on the mental states of agents, like beliefs and intentions, as in FIPA SL, this approach defines interactions based on the creation, manipulation, and satisfaction of social commitments between agents.
Can you give an example?
A commitment typically has a debtor, who is committed, a creditor, to whom they are committed, and content, what the debtor is committed to do. Protocols define rules for how actions create or discharge these commitments. For instance, Agent A requesting Agent B to do task X might lead to B creating a commitment to A to do X if B agrees.
So it tracks obligations between agents.
Exactly. And these protocols can often be modeled using formalisms like extended finite state machines or specialized commitment machines like generalized commitment machines, GCMs, which track the state of commitments.
How do we ensure these complex protocols actually work as intended?
Again, formal methods are key. You can use formal specification languages, things like desire, Z, SDL, ISPL, to precisely describe the protocol rules. Then you can use verification techniques, especially model checking, to automatically analyze the protocol for desirable properties.
Like
Ensuring the protocol eventually terminates, that agents don't get stuck in deadlocks, that certain commitments are always eventually fulfilled, or that delegation mechanisms are clear and unambiguous.
So for meta AI needing to delegate tasks between components, which approach is better, FIPA ACL or commitment-based?
They both have strengths. FIPA ACL offers standardization and well-defined semantics based on mental states. Commitment-based protocols can be more flexible and arguably model the dynamics of delegation and agreement more directly.
A trade-off then.
Often, yes. But the crucial point for advanced AI is the need for formally specified communication, regardless of the exact approach. You need that precision and the ability to verify correctness, especially for critical tasks. Emergent communication, where agents develop their own signals, is generally not suitable for reliable, precise delegation in these systems.
Too unpredictable.
Exactly. So the implications for meta AI are a potential trade-off between standardization, like FIPA, and flexibility, like some commitment protocols, the absolute necessity of formal specification and verification for reliable delegation, commitment protocols being well-suited for managing the dynamics of who owes what to whom, and the general requirement for communication languages with clear, unambiguous semantics.
This emphasis on formal languages keeps coming up. Let's maybe broaden that slightly. Why are formal languages in general considered so important for advanced AI development compared to, say, natural language?
The core difference lies in precision. Formal languages think programming languages, mathematical logic. Specialized specification languages, like the ones we just mentioned, have precisely defined syntax and semantics. There's no ambiguity about what a statement means.
Unlike natural language, which can be fuzzy or interpreted in multiple ways.
Exactly. And that precision brings huge benefits, especially when building complex, high-stakes systems like advanced AI.
What are the main benefits?
Clarity and unambiguity, as we said. Verification and validation, because the meaning is precise. You can mathematically prove properties about the system or automatically check if a model satisfies certain requirements. Automation formal specifications can sometimes be used to automatically generate code, test cases, or even perform automated reasoning.
Okay.
Knowledge representation is another big one. Formal logic and ontologies, often expressed in languages like OWL, Web Ontology Language, allow AI systems to represent complex knowledge in a structured, machine-understandable way. The Hypersia system, mentioned in the Meta AI research, uses a formal language called Kiklang for this.
And efficiency.
Yes, sometimes formal languages can be more concise and efficient for communication between AI components compared to parsing lengthy natural language, reducing overhead.
Sounds great, but are there downsides? Why not use formal languages for everything?
Well, there are challenges. It usually requires a higher initial effort to create formal specifications. It demands specialized expertise, which isn't always available. And sometimes capturing fuzzy, informal user requirements purely in formal terms can be difficult.
So it's about using them in the right context.
Precisely. For developing the core AI system, especially safety-critical or trustworthy systems, the trend is towards more formal methods, not less. There's even a field called AI for Formal Methods, AI4FM, exploring how AI can help create formal specifications.
Interesting. What about agent communication?
As we discussed, formal ECLs are generally preferred for inter-agent communication for clarity and interoperability, though sometimes structured data formats generated by LLMs can offer a practical middle ground. Natural language is usually reserved for the human-AI interface.
And language learning itself. Does that offer any insights?
There's an interesting analogy. Some research suggests that learning structured formal representations can actually enhance the effectiveness and robustness of language models, hinting that formal structure might be beneficial even when dealing with natural language processing.
So, implications for meta AI architecture, formal languages seem unavoidable.
For the core components, knowledge bases, reasoning engines, communication protocols, yes, I think formal languages are pretty much a necessity due to the complexity and the need for reliability.
They enable advanced capabilities.
Right. Things like automated reasoning about the system state, formal verification of safety or ethical properties, structured self-monitoring, these rely on formal underpinnings.
Efficiency gains too.
Likely, yes, especially for the internal communication between components, but you'll probably see a hybrid approach. Formal languages internally, potentially combined with more informal or natural language interfaces for human interaction.
Okay, we've covered self-awareness, dynamic structures, communication, formal languages. How do we know if a meta AI system built with all this complexity is actually any good? How do we evaluate its overall effectiveness and cohesion?
That's a huge challenge. Effectiveness is about whether the system achieves its intended purpose, its goals. Cohesion is about how well the different parts work together, how interconnected and aligned they are towards those shared goals.
Measuring the whole system, not just individual parts.
Exactly. And we can draw on metrics from related fields. Multi-agent systems, MAS research offers a lot here.
Like what?
Standard performance metrics, obviously. Task completion time, success rates, throughput, resource usage, overall system utility, but also things specific to distributed systems. Scalability, robustness, how well does it handle component failures, maybe measured by recovery time. Adaptability, how quickly can it adjust to changes.
And metrics specifically about the teamwork.
Yes, coordination and collaboration metrics. Communication efficiency, latency, overhead. Decision synchronization, are agents making consistent choices? Task allocation accuracy. Measures of cooperation effectiveness, are they genuinely helping each other?
How do you measure something like cooperation?
It's tricky. Sometimes you look at knowledge similarity between agents. Are they developing shared understandings? Techniques using cosine similarity on their internal representations or comparing local explanations generated by different agents have been explored.
Okay, what about other fields? Distributed computing.
Distributed computing and computer-supported cooperative work, CSCW, offer relevant ideas too. Frameworks that consider the task, the group structure, the social protocols, and the technology used.
More concrete metrics.
Interaction metrics, frequency, patterns, timing of communication, shared artifact metrics, how well the agents manage shared resources or data, things like concurrency control, and various performance and quality metrics like accuracy, precision, recall, ranking measures, and even normalized distance-based performance measures, NDPM, that compare the system's output to an ideal output.
What if humans are part of the team? Human AI teaming.
Good point. If humans are involved, evaluation needs to go beyond just task performance. Human AI teaming, HAIT research, focuses on the quality of the interaction.
So what do HAA metrics look like?
Key things include trust calibration, is the human's trust in the AI appropriate? System transparency and explainability, adaptability of the team. Shared mental models, do the human and AI understand the situation similarly? Human satisfaction, collaboration, effectiveness.
Also things like complementarity.
Yes, is the team effectively leveraging the different strengths of the human and the AI, and human confidence in the AI's judgments? There are frameworks to help select the right HAI-CATE metrics depending on how the human and AI are collaborating.
One more area, software architecture principles. Do they apply?
Absolutely. Concepts like coupling and cohesion are very relevant.
Remind me.
Coupling measures the interdependencies between different components. You generally want low coupling, so changes in one component don't ripple through the whole system. Cohesion measures how related the elements within a single component are. You want high cohesion components should focus on a well-defined set of tasks.
So keep components independent, but internally focused.
That's the ideal for maintainability, understandability, robustness, efficiency, and scalability. These principles definitely apply when designing the architecture of a complex meta AI system.
Okay, pulling this evaluation thread together for meta AI, what's the bottom line?
You need a multifaceted evaluation strategy. No single metric will do. It has to combine MAS performance and coordination metrics, software architectural principles like low coupling and high cohesion, and if humans are involved, HAI metrics focusing on the interaction quality.
And this idea of cohesion is central.
Yes, particularly task cohesion, ensuring that the actions of individual components are genuinely aligned with and contribute to the overall system goals. It's about making sure the team is pulling in the same direction. A summary table mapping evaluation goals to specific metrics could be really useful here.
Right, a comprehensive scorecard. Now, we've touched on trust and reliability. Let's explicitly talk about ethics. How do you build ethical principles right into these advanced AI systems?
It's not just an add-on, it's becoming an imperative. As AI gets more powerful and influential, concerns about bias, lack of transparency, potential misuse, privacy violations, and causing harm are growing louder.
So we need AI that behaves ethically.
Exactly. This leads to the field of machine ethics or computational morality and ethics, CME. The goal is to design systems whose behavior is, well, morally acceptable.
How do you formalize something as complex as ethics?
That's the challenge, but formal methods offer pathways. Deontic logic is one approach.
And
Logic of obligation, permission, and prohibition. You can write formulas like agent A is obligated to ensure property P, or action X is forbidden if condition Q holds. It allows specifying ethical rules formally.
Okay, other logics.
Temporal logic is useful for reasoning about ethical properties over time. For instance, it must always be the case that if a critical event occurs, a warning is eventually issued.
Specifying behavior sequences.
Right. You can also encode ethical theories directly as formal rules or constraints, like encoding deontological rules, duty-based ethics, or utilitarian principles, maximizing overall good, as logical axioms.
What about disagreements? Ethics isn't always clear-cut.
That's where formal argumentation comes in. You can represent conflicting ethical viewpoints or principles as arguments and counterarguments within a formal framework, allowing the system to reason about trade-offs.
So once you have these formal ethical specifications, can you automatically check if the AI follows them?
That's a key goal. Automated verification techniques, like theorem provers and model checkers, can be used to mathematically prove that an AI system's design or behavior satisfies the formalized ethical properties.
Proving ethical compliance.
Or at least verifying compliance against the specific formal model. There are proposals for things like an ethical firewall architecture, where safety or ethical constraints are enforced and compliance can be formally verified. You can also evaluate the AI's outputs automatically for things like factual accuracy, bias, harmful tone, fairness criteria, etc.
What happens when the AI faces a genuine ethical dilemma where rules conflict?
That's tough. Several strategies exist. Argumentation-based reasoning, as mentioned, can weigh conflicting values. You might define explicit prioritization rules. Safety overrides efficiency.
Learning from data.
You can try to learn ethical preferences from data, like the moral machine experiment did, but relying solely on descriptive ethics, what people do think, rather than normative ethics, what they should think, is problematic.
Other option.
Randomization in truly balanced dilemmas. Some speculative ideas involve rebel agents that intentionally challenge norms to highlight issues. But realistically, for complex dilemmas, human oversight and intervention are often necessary.
How does all this connect to the broader idea of trustworthy AI?
Trustworthiness is a multifaceted concept. It includes validity, reliability, safety, fairness, security, resilience, transparency, accountability, explainability, privacy enhancement. Building informal ethical reasoning and verification directly supports many of these pillars, especially safety, fairness, transparency, and accountability. Adhering to ethical guidelines is fundamental to trustworthiness.
So, for meta AI, what are the key implications regarding ethics?
Formal methods, especially deontic and temporal logics, seem crucial for precisely specifying and verifying ethical constraints in these complex, multi-component systems. Explainability isn't just nice to have, it becomes an ethical requirement, and formal reasoning can help generate those explanations. Comparing different formal approaches, like logic versus argumentation, reveals trade-offs in expressiveness and computational cost. A table comparing these might be helpful.
Okay, one last major area. Architecture.
Hmm?
How do you structure these complex meta AI systems? Centralized control, decentralized, something else?
This is a classic question in multi-agent systems. You have centralized architectures, where typically one component has a global view and makes key decisions or coordinates others. Think of traditional air traffic control.
One boss.
Right. Then you have decentralized architectures, where control is distributed among autonomous agents, often interacting based on local information and simple rules. Think of swarm intelligence in insects, using stigmergy in direct communication through the environment.
No central controller.
Exactly. And there are trade-offs. Centralized systems can potentially achieve global optimization because one entity sees the whole picture and coordination is simpler. But they can be bottlenecks and have a single point of failure.
If the center goes down, the whole system fails.
Correct. Decentralized systems are often more robust. Losing one agent doesn't kill the system and they scale better. But coordination is harder, and agents making decisions based only on local information might lead to suboptimal overall behavior.
So, neither is perfect.
Generally not for complex systems. That's why hybrid architectures are very common and highly relevant for meta AI.
What kinds of hybrids?
Hierarchical control is one, different levels of agents, with higher levels delegating tasks to lower levels. You see this in organizations.
Makes sense.
In multi-agent reinforcement learning, there's centralized training, decentralized execution, CTDE. Agents learn a coordinated policy together using global information during training, but execute actions based only on their local observations during deployment.
Best of both worlds, maybe.
Tries to be. Market-based control is another hybrid, using mechanisms like auctions or contract nets where agents bid for tasks or negotiate agreements. This decentralizes allocation but within a structured market framework.
Like an internal economy?
Sort of. Holonic architectures are also interesting. A holon is something that is simultaneously a whole, autonomous, and a part-dependent element of a larger system. Holonic systems are recursive hierarchies of these holons.
Complex structure.
Yes. And you can also have mixed protocols where some interactions are centrally coordinated while others are handled decentrally.
So for meta AI, what's the likely architectural direction?
There's probably no single best architecture. It'll depend heavily on the specific application and requirements. The key is balancing conflicting attributes like global optimality versus robustness, coordination, simplicity versus scalability.
Hybrid seems likely.
Very likely. Models inspired by hierarchical control, CTDE, or holonic concepts seem particularly relevant for managing the complexity while retaining some robustness and scalability.
And coordination is still vital.
Paramount, regardless of the architecture. Effective mechanisms for information sharing, task allocation, and conflict resolution are crucial. Even in mostly decentralized systems, you need good coordination protocols. For complex meta AI, having decentralized elements will likely be critical for scalability and resilience. A table comparing these architectures and their pros-cons for meta AI could summarize this well.
Wow, okay. We have covered a lot of ground today. From AI thinking about itself to dynamic internal structures, formal communication, evaluation, ethics, and architecture. It really paints a picture of incredible complexity.
It definitely does. These advanced AI systems, especially the meta AI concepts, are far beyond simple algorithms. They involve intricate interactions between potentially many specialized components.
So the key takeaways for our listeners trying to get a handle on this.
I think understanding these core elements, metacognition for self-improvement, formal methods for precision and dynamism via things like placebo pipes, clear communication protocols, multifaceted evaluation, embedded ethics, and hybrid architectures gives you a really crucial framework.
A framework for navigating this rapidly evolving field.
Exactly. It helps cut through the hype and see the underlying engineering and conceptual challenges being tackled.
It certainly feels like we've built up a much clearer understanding today. Thanks for breaking it all down.
My pleasure. It's fascinating stuff.
So maybe a final thought for our listeners to chew on. As these systems become more self-aware, more dynamic, more capable of complex coordination, and even ethical reasoning, how does that change our relationship with them?
That's the million-dollar question, isn't it? Are we moving towards AI as tools or AI as genuine collaborators? And what does collaboration look like with an entity that might restructure itself or reason about its own goals in ways we're only beginning to understand?
Big questions indeed. Which of these areas, self-awareness, formalization, ethics, architecture, feels most critical or maybe most challenging right now? Something to ponder.
Definitely. And if this has sparked your interest, digging into the meta AI research or work on computational metacognition or formal methods in AI would be a great next step.
Absolutely. We hope this deep dive has given you those aha moments and a solid foundation for understanding advanced artificial intelligence systems. Thanks for joining us.